Hello guys, how are you? Welcome. We are looking in this lesson, it's actually a tutorial on differential calculus. In the second tutorial, we are essentially looking here at the applications of differentiation. Your question papers, your examinations always have a question or two on applications of differential calculus. Okay, I'm going to take you through a few questions. Essentially, it's to demonstrate the principle. So just about 4 questions should actually be enough to show you how we actually use the knowledge that we gained in our lesson to tackle problems. Okay, I've got a paper here, 2008. So it's a tutorial. Again, calculus 2. Okay, I've got a 2008 paper. Question number 10, 2008, November, paper 1. Question 10 it says, a drinking glass in the shape of a cylinder must hold 200 ml of water, or rather of liquid, must hold 200 ml of liquid when full. And there's a diagram which is given. It's essentially a cylinder. Excuse my drawing. Center, radius r, height h. Then question 10.1, show that the height of the glass h can be expressed as h equal to 200 over pi r squared. That's 2 marks. 10.2, show that the total surface area of the glass can be expressed as SR. S is a function of R, so it's actually the surface area is a function of the radius of the glass, equal to pi r squared plus 400 over r. Over r, that's for 2 marks again. There's a third question, but for purposes of space, let's deal with the above 2, then we'll look at the third question. Okay? Right, guys? As good students all the time, what we do is to understand the question. So let's go through the question, again, and understand. When full, excuse me for that. A drinking glass in the shape of a cylinder, so it's something of this nature. A drinking glass in the shape of a cylinder, I think that actually gives us a very good example. Must hold 200 ml of liquid when full. 200 ml of liquid, we are talking of volume here. It must hold a volume when full of 200 milliliters. That's fine. Then, of course, we are given the shape, which I'm trying to mimic using this. I'm sure it's actually something very similar. and we are given dimensions. H obviously represents the height of the glass. Say from here, from one end to the other. And R represents our radius. So from the center to the edge, we can see that the base, because it's actually a cylinder, has to be circular in nature. Okay? So, show that the height of the glass can be expressed as h equal to 200 over pi r squared. There's two things. Okay, there's the first thing that I actually want you to see. Look, somehow we're talking of pi r squared. What comes into your mind when we talk of pi r squared? It's area, isn't it? Area of a circle. Where is the 200 coming from? We have been told the volume that this glass must actually hold when full is 200. So don't you think we're probably getting this from the volume of the glass? If you manage to find the volume of this glass, then we should probably be in a position to express our H in this form. So let's check. How do we calculate the volume of a cylinder? Given a cylinder like this, it's obviously, for us to find the volume, is the cross-sectional area, the cross-section for a cylinder here, cross-section multiplied by height. Our cross-section is actually a circle, it's a circle. So for us to find this area, it has to be pi r squared. Then of course, multiplied by the height, we'll get the volume. So we can confidently come and write 10.1 volume of cylinder. One, we have been told that the volume is 200 mils. Right? More importantly, or the volume that the cylinder can actually hold is 200 mils, which is actually the volume of the cylinder in itself. More importantly, we also know that looking at the shape, the volume of the cylinder has to be the cross-sectional area. We've got a cross-section which is actually a circle, and we've been told that the radius is r. So, cross-sectional area pi r squared multiplied by the height of the cylinder. That will give us our total volume. Sorry my shape, but essentially we are saying that the cross-sectional area multiplied by the height should actually give us the volume. And if we do that, then we should notice immediately that since our volume, just expressing it in terms of dimensions, is pi r squared h, we are told what the volume is 200. So we can confidently write that pi r squared h, the volume, is equal to 200, because we've been told that's the volume. Now, if we do have this now, what then should we do? We want to express h in terms of r, or rather want to have h as our subject, as required by the question. How do we make h our subject? Divide both sides by pi r squared. And we end up with h is equal to 200 over pi r squared. That's what the question requires. So we have shown that. So we can express the height given the volume of the cylinder. We can express the height as a function of r, or rather in terms of r. Okay, so that actually does it for question for question 10.1. You can see it's 2 marks. That's why we actually don't have so many marks there. It's a very simple something to show, really. It's a simple thing to show. Let's go to question 10.2 and see how we can actually, if we can actually show that as well. Now question 10.2 says, show that this total surface area of the glass can be expressed in the form S surface area equal to pi r squared over 400, or rather plus 400 over r. Okay, how do we find the surface area of a cylinder? Guys, it's actually very easy. I'll show you how to do it. if I were to make this into something that looks like a cylinder, I hope you can see, right? When we talk of surface area, we are talking of the area of the surface, right? If my cylinder is actually covered on both sides, then it will be this area, that area, that area. How do we find this? So let's talk first. This area we know we can easily find. This will be the area of a circle. That's fine. How do we find the area now of the outer part, or rather of the curved part? It's easy, right? Check. If I were to open up my cylinder like that, you will notice I'm going to essentially come up with probably something which looks like a simple rectangle, assuming of course that I'm not having the other two ends. But what is so special about that? If you check, when I'm having it like this, when I open up, this side is essentially what was the circular part, originally. So if I manage to find the perimeter, if I manage to find the length of this, which is actually the simple circumference of this circle, I will have found the length of this side. What about this other end? What about this side? Again, if you check, if this is my circular part, then this actually becomes my height. So when I open up, I have got my original circumference, then I have got my height. The important thing though to realize is, when we are talking of, in this case, we are assuming of course our cylinder or our glass is actually closed at the bottom. That's number one. If it's a drinking glass, then we obviously have to assume also that it's actually open at the top. So when we open this, when we're talking of the surface area, then we are talking of this whole surface, which we've just shown you, is a simple circumference or length of the circumference and the height. Then of course we have to consider the length of this, or rather the area of this base. What do I mean? I'm saying when we open up this cylinder, we are going to essentially have the following. What was originally, our circumference, then we are going to have, our height, so it's a simple rectangle, but more importantly, at the base, remember, we also have the circular part which was covering that. So we also need to consider this surface area too. Question now, how do we calculate these surface areas? One, the area of a circle is a simple pi r squared. So the area of the base, the surface area of the base will be this simple pi r squared. But the question now is, what about the area of the curved part that I just showed you? And we are saying, if we open that thing up, we are going to end up with one side being this original circumference we open up, and the other one being the height. So we know one is going to be h, the other one, if we look the circumference, how do we calculate the circumference of a circle? The circumference of a circle, c, is equal to 2 pi r. So the length of this side is actually 2 pi r. Right? More importantly, you see also that your h, if you look at your expression as given, there is no h anyway. But if we go back to question 1, we just managed to show that h is equal to 200 over pi r squared. So we can easily come here and remove this h, but we know that h is equal to 200 over pi r squared. Isn't it? So now, if we want to talk now of the area of the curved surface, then it will be that by that, and it's simple area of a rectangle. So it will be 2 pi r multiplied by 200 over pi r squared. You agree with me? Our pi will cancel, our r will cancel as well, so we are actually going to remain with 200 over r by 2, so 400 over r. But then we are saying that the total area, we have to consider the base and the curved surface. So our total surface area, therefore, as a function of r, will be equal to this area, pi r squared, plus this area 2 by 200, 400 over R, which is exactly what the question requires us to show. So we've just managed to show that the surface area of this glass of ours can actually be expressed as a function of the radius, or in terms of the radius, as surface area equal to pi r squared plus 400 over r. Now, we now look at the third question which is there. I said we actually didn't put it down because we wanted to save space, or rather we didn't have space. Now that we do, let's look at that question and see if we can actually solve it as well. So, we've just been asked to show that the surface area is pi r squared plus 400 over r. And then, question 10.3 says, after you've done that, go on now to show, in fact it says, hence, determine the value of r for which the total surface area is a minimum. Yeah. That's for 5 marks. Okay, we will answer that. But let me just probably go on and digress a bit. Why will it be important for us to find a value of R for which the surface area of the glass is actually, some minimum value? If we can have such, if we can have the minimum surface area possible, but still have our glass holding the same volume of water or the same volume of liquid, then one, we'll be saving ourselves. Look, you can imagine, you can think of people who actually produce this. We can save ourselves. Suppose we need to come and paint this glass as an example. We need to come and paint the surface. If we make it a minimum, then if we're producing thousands and thousands of this, imagine how much paint, how much money we actually save ourselves, and so many other things. So it's actually a very good application of calculus. I'll show you just now why this actually has to be solved through differential calculus. So let's try to look at this. What is the question saying? Determine the value of R for which the total surface area is actually a minimum. What do we know from our differential calculus? We know that we can talk of stationary points, we can talk of minima, we can talk of maximas by simply understanding that at a minimum turning point, at a stationary point, at a maximum turning point, our derivative is always equal to 0. That's an important thing. And all we have to do here is we are given the surface area expressed, or rather as a function of R. So if we find the derivative of S with respect to R and equate that to 0, we've just found the value of R, which is actually going to allow us to, or which is actually going to give us the minimum surface area of the glass. So what do we do then? We say, okay, we know that S as a function of R is equal to pi r squared plus 400 over R, right? If that is the case, if we are going to find the derivative, the gradient function of S in terms of R, then we will say d ds dr, because we are actually differentiating with respect to R. Our independent variable here is actually the R, will be equal to, how do we differentiate? Our variable is R, so here, in fact, let's write it actually in a much better form first, the standard form that I always talk about. We can rewrite our SR, or S as a function of R, equal to pi r squared. Here where we have got 400 over R, we understand that 1 over R is the same thing as R to the power minus 1. So we can write this as plus 400 R to the minus 1. Now, we can now easily go on to differentiate this. ds dr will be equal to our power here of R is 2, our coefficient is pi, we multiply the 2, we get 2 pi. reduce your power by 1, we get r to the power 1. Then here, plus, our coefficient is 400, our power is minus 1, so minus 1 by 400, we'll get minus 400. Then reduce the power by 1, so we've got r to the minus 1, then minus 1 again. So we're going to end up with r to the minus 2. So all of a sudden now, we are sitting with ds dr is equal to 2 pi r minus 400 over r squared. But is that enough? No. What do we need? How do we find the value of r? Or the values of r where we're actually going to have this as a stationary, or where we're going to find either the maximum or minimum or any other stationary point. We simply say at that point our gradient has to be 0. At a stationary point, either at a minimum or at a maximum, the idea is that